So this is the third lecture on frequency response. Last time we had looked at the frequency response of the common source amplifier, and I had also looked at approximation techniques for finding the minus 3 dB frequency. Today in this lecture we look at common gate and source follower configuration. So let's begin with the common gate. So this is the simplest common gate configuration. Actually it's not the simplest because I have added an RS. Without RS it is far too simple, so this is a little more realistic. In fact, when we did this low frequency small signal analysis of the common gate, I had not put RS, but now I have added RS. So let us find the VO over VI at high frequencies for this common gate configuration. To simplify, here in this lecture we'll neglect the RO of the transistor, which will come in parallel with the current source. You should do this at home, include RO and then find the transfer function. So here again you should pause and find the transfer function. I would suggest without RO and with RO and then continue. So here in any case C1 is CGS plus CSB and C2 is CDB plus CGD. I'm continuing with the analysis. So we write two nodal equations, one at Vs and one at Vo. I will just quickly go through this. So at the output node, Vo by Rd plus SC2 Vo minus GMVS equal to 0. Then you multiply the whole equation by Rd as I always do, so that there is no fraction left. And then this has only Vo and Vs, so one can find Vo in terms of Vs. GMRD by 1 plus SC2RD into Vs. And at Vs, we get another equation, SC1 Vs plus Vs minus Vi by Rs plus GMVS equal to 0. This equation has only Vs and Vi, there is no Vo. The reason this has happened is because there is no RO. Because there is no RO, there is no Vo term in the nodal equation at Vs and no Vs term in the nodal equation at, there is a Vs term actually, but there is no Vo, so that's why these equations are simpler. So we multiply by Rs and then find Vs in terms of Vi from this second nodal equation, and then we substitute for this Vs here and we get Vo in terms of Vi. So you get Vo over Vi equal to 1 over 1 plus GMRS plus SC1RS into GMRD by 1 plus SC2RD. That's just the product of these two terms, this term and this term. Now let's rearrange in what I have called the standard form, which is to take out the low frequency gain, and the S terms will be of the form 1 plus S into something. In this case there are two first order terms. Typically there will be one big long polynomial in S, with the S raised to 0 term being equal to 1. So you get GMRD over 1 plus GMRS. We get this, then I am rewriting this. If you look at this carefully, Rs over 1 plus GMRS is actually Rs in parallel with 1 over GM. You can convince yourself, it's quite straightforward. So this directly actually tells us that the resistance seen by C1 is Rs parallel 1 by GM, and the resistance seen by C2 is Rd. So let us look at that. Go back and look. So the resistance seen by by C2 is Rd here, and the resistance seen by C1, so we'll short the Vi, so we'll get Rs to ground in parallel with the resistor looking up the source of the MOSFET, which is 1 by GM if there is no RO. So that's how 1 by GM parallel Rs comes in this equation. Alright, so this is the equation. Let's make some observations. If Rs is 0, which is the case we had considered in lecture 15 slide 8, then the gain is GMRD. which is the same as the gain of a common source stage. And we had noted that there also, that with Rs equal to 0, the gains of the common source and the common gate stages are the same, almost the same. With Rs, of course, the common gates gain is much lesser because loading happens due to Rs. Here the two poles have come out independent, and kind of alluded to that earlier, because we've ignored RO, and so that the interdependence of VO and VS was removed. It's not a bad assumption if RS and RD are small compared to RO. If they are not, then of course one has to include RO. So let's go back to that's where is it? This one. So if RD, for example, is a PMOS, which is more often the case, then it will not be possible to ignore the RO of M1. But in this case, it is okay to ignore. RS typically would be, well, RS in this circuit could be the source resistance of the incoming signal in a communication circuit, or it could be the output resistance of a common source stage, which will happen in a cascade, perhaps. Yeah, one could think of it that way. Yeah. Okay, anyway. So we get two independent terms, and so the poles are kind of directly available to us. Also, very important observation that distinguishes the common gate stage from the common source stage is that there is no capacitance between the source and drain of a MOSFET, and therefore for the common gate stage there is no Miller capacitance. There is no for a common gate stage, the source is the input, the drain is the output. There is no capacitance, so there is no Miller effect, and because there is no Miller effect, the overall capacitances in a common gate stage are smaller compared to the common source stage, and because of this, the frequency response of a common gate stage is typically always better than the frequency response of a common source stage. Alright, so this is of course one reason why common gate is used in RF circuits also. CS is also used, but CG is also used, and we'll see how this also affects the response of the cascade in the next lecture. Alright, I've put some values, numericals. I think I had used these same numericals in the last lecture for the common source stage, so that we can compare across the various amplifier stages the frequency response. So GM is 20 milliamp per volt, RD is 2 kilo. I have put RS 0 just to do a comparison, a kind of an idealistic comparison. So the voltage gain is 20, which is the same as for a common source stage, and the capacitances are 10 pico, 4 pico, 5 pico. With that, the poles come out. So I've called this P2 because that is a larger frequency. P1 is the smaller frequency. So C2RD, the output pole, is the dominant pole for a common source stage, because at the input the resistance is very small. It is effectively 1 by GM. So the pole is at a higher frequency. Alright, so do a quick comparison between common source and common gate. The gains are the same if RS is 0. So that is the case I have considered for the numerical example. The dominant pole for a common gate is much higher than for the common source, and you can see this is the Miller, this GMRD CGD is the Miller capacitance in a common source, while there is no Miller capacitance here, and therefore, so you can see CGD-RD, CGD-RG is a same order if you assume, then there is an additional GMRD here which pulls down the dominant pole frequency. The second pole frequency is also a little higher in the common gate compared to the common source, but that is all very variable depending on the actual parameters and numbers. Okay, let's look at the source follower. So the input at the gate and again with a gate resistance and the output at the source. So again please pause and solve this circuit and find VOS over VIS. Alright, so here is a small signal circuit. Again, I am ignoring RO of the MOSFET for simplicity. You should include it while you solve. Why am I going on saying you should solve with RO? It is because learning to draw and solve high frequency small signal circuits and finding transfer functions is something you must practice and you must solve. I would say about 10 different circuits actually from beginning to end, finding the high frequency transfer function, because when you solve a few of them, then you kind of get a hang of how to write the nodal equations, how to simplify them. You start that the pattern starts emerging, and you learn that pattern if you do this many times, and you must do this. This is something I've said it before. This is a skill you must acquire in this course. Alright, so here are the capacitances. So there is a CGD from gate to ground, CGS between the input and the output, and CSB from output to ground. Output of course is at the source. So again there are two nodes, so we write two nodal equations. Let me quickly go through them. So at the output node, VO over RS plus SCGS into VO minus VG plus SCB into VO minus GM VGS or plus GM VSG, and VS is VO, so we get plus GM VO minus VG, and multiply by RS, and there is only VO and VG in this equation, so you can find VG. excuse me. So you get VG in terms of VO, and you write an equation at the input VG minus V in by RG plus SCGD VG plus SCGS VG minus VO, multiply by RG, and you'll get VG something minus VO something equal to V in, and then we substitute for VG in terms of VO from the first equation, so we can find VO in terms of V in. So this equation is kind of long, which is good. You must learn to do this, and of course you should even include RO and do this, so it will be even longer. So I'm not going through this algebra, you should go through it yourself. Eventually this is the transfer function we get. So let us look at this transfer function. So VO by V in, so again I have written it in a standard form. Low frequency gain is GMRS over 1 plus GMRS. We had arrived at one form of this when we did the low frequency AC analysis. Of course, we have consistently ignored GMB here also. Ideally, GMB should be included. So this is of course approximately 1, but always less than 1 GMRS by 1 plus GMRS. There is a 0 in this transfer function, and of course there are two poles. Let me talk a little about the 0. So this is SCGS by GM. So a 0 occurs in a transfer function when there is a path between the input and the output that is parallel to the main path. There is a capacitance here between the input and the output. That is why a 0 occurs. So let me go back to the this circuit. Yeah. So there is a CGS between the input and the output, the capacitance. That causes a 0. It is in parallel with the main path for signal to flow, and the main path is of course through the transistor, that is through the GM. A gate change in gate voltage changes the current, and that changes the output voltage. But a change in the gate voltage also changes the current in the gate source capacitance, and that causes a 0. We had a 0 in the common source stage also. There of course it was a CGD that was causing the 0. In a common gate there was no capacitance between the input and the output, and therefore there was no 0 in the transfer function. right? So remember that that is what causes a 0. Here the 0 is in the, let us see, it is a 1 plus SCGS by GM. So this is a 0 in the left half plane. It's a negative value. For the common source stage, it was 1 minus SCGD by GM, because there was an inversion between the input and the output nodes in the common source stage. Razavi has a nice small section on finding the expression for the 0 without solving the transfer function. I don't use it much, but it's a very nice, nifty method. So I suggest that you go through Razavi and learn that method of finding the 0. The fact that the 0 is GM by CGS. You can find this expression GM by CGS without deriving the transfer function. So please go through Razavi to understand that method. Okay, there are two poles, and let us look at them. So same values, numerical values I have put: 10, 4, 5, 20 milliamps per volt, and RSRGR 2 kilo ohms. We do this A and B. A is the coefficient of the first order term, B is the coefficient of the second order term. So this is A. Now if we look at this, and if in fact we put numbers, we see that this is 8, this is 20, 30, 40. So this will be 0.5, 20 by 40, and this will be 0.75. So these two are slightly smaller than the first term. So the first term dominates in the dominant pole. So the dominant pole, especially with these numbers, is determined by CGD times RG. Although these are not much smaller, but they are reasonably small. So in fact, and you can see that CGD is always small in any MOSFET in saturation compared to CGS and CSB and all that, and therefore this the A is going to be a small number, and so the dominant pole of the common drain or the source follower is at a high frequency, because the time constant is small, right? That's the characteristic of the source follower. The second, the B, which gives the second pole, if you look at the numbers 50, 40, 20, all three are about the same. So it's difficult to make approximations. All capacitances contribute to the second pole. All right, it is very difficult to say, give any simplification. All right, so with these numbers we get P1 and P2, the values are 17 megahertz and 134 megahertz. Okay, perhaps you would ask the question as to, can we apply Miller's theorem for the emitter follower circuit? It is not very advisable. It is doable, and so I am saying you try it. It works, but it's a little tricky. So I would like you to try it yourself, apply Miller's theorem. So where do we apply Miller's theorem? In any case, to CGS, right? The Miller's theorem is applied to any capacitance connected between two nodes across which there is a voltage gain or whatever. There is a VO over VG. There is no gain here nonetheless. Actually, because there is no gain is why this is a little unadvisable to apply Miller's theorem. But just for the heck of it, you should apply to learn what it is like. It works, as I said, but it's tricky. Also, for whether with Miller or without Miller, suppose we wanted to find the dominant pole by the open circuit time constant method. Again, this is an interesting exercise for the source follower, and I am saying you try this at home. Right? It's a good exercise to find P1 by the open circuit time constant method, and once you find it, you compare it with this, which is the more exact expression. All right. In fact, this gives you an idea about In fact, here is 3 time constants. But so you find them without referring to this expression, you find the time constants and find P1. Alright. Okay, so here's a comparison of all 3 stages, CS, CG, CD. CS, CG we already did. I've added CD. The gain of course is approximately 1. The dominant pole is the highest of all 3 and the second pole is somewhere in between. Overall, the source follower frequency response is far better. That is, the dominant pole is at a much higher frequency compared to the common source and common gate. And so, whenever there is a cascade of multiple stages, so there may be a common source, common drain, or common source, common gate, common drain, any combination, generally one tends to ignore the frequency components caused by the common drain or the source follower because they are always at a higher frequency. The common source of course dominates, but common gate also plays a role. Generally this is ignored. Alright, it is just a rule of thumb, not to be taken too seriously. One should always find, but as a first approximation it is okay to ignore the source follower frequency response in a multi-stage amplifier configuration. Alright, so that's the end of this lecture. Next lecture we'll see the frequency response of cascode and various differential amplifier configurations.